The objective of this lab is to analyze the motion of a star using the data points provided in the CSV file and to calculate the net force acting upon the star from a black hole at a given position. The calculations of the computational model occur under the assumption that the only force acting upon the star is that from the black hole. The calculations are determined using the physics principles laid out in the law of universal gravitation and Newton's second law. Every data point is calculated given the delta t of one day, and the mass of the star is relevant when calculating using the universal law of gravitation. Before these calculations can be made, however, a small loop is run through that takes in the data points from the CSV file and computes the velocity vectors. This line finds a difference between the first and the second x values and then divides this by delta t, given that velocity is the change in position over the change in time. The same thing is then done for the y values to find the y component of velocity. These computed values are then put into vectors and used in the next step of calculations. This while loop is where the real mass calculations are performed. The first part takes in the velocity vectors we just calculated and sets values to the initial and final velocities. Here. Using the formula momentum equals mass times velocity, momentum for each is calculated. Changes in both are then calculated here. dp dt is calculated given that it is the change in momentum over the change in time, or delta p over delta t. Newton's second law states that the net force on an object is equal to the rate of change, that is the derivative, of its linear momentum p. So we can set the net F net equal to dp dt, as you can see. This next step uses the equation of dp dt equals p hat times the magnitude of p, or the change of the magnitude of p over the change in t, times p hat, plus the magnitude of p times dp hat over dt, given that this is a parallel component and this is a perpendicular component. Since p hat is a unit vector, we can calculate that by dividing each value by the magnitude. Then the change in the magnitude is divided by delta t to give the change in magnitude of p over delta t. To get the parallel component, we then multiply this by p hat, as we saw in the equation before. Using Newton's law again, the perpendicular component is found given that F net is F parallel plus F perp. Using subtraction, we're able to solve for the perpendicular component and then set this equal to F net, using Newton's second law once again. Finally, the universal law of gravitation is used to calculate the mass of the black hole. The distance or radius is found between the star and the black hole using magnitude, and the final mass is calculated with this formula and outputted and saved. This is the graphical representation at the end of the orbit. In the beginning, the parallel and perpendicular components were larger, but as the star moved closer in orbit to the black hole, the magnitude of F net increased, as you can see. In the end, the final mass of the black hole was over 12,000 times as big as the star. In an attempt to address the accuracy, I inputted every calculated value of the black hole as it ran through the loop into Excel, and I found the average. This value was not significantly different, as you can see, than the final mass that I outputted, and both were within the window of error allowed by WebAssign. While both FNet and dpdt have the same value, as given in Newton's second law, dpdt is the calculable result of FNet. We can observe the impact of FNet that has on the system and its surroundings, but we cannot actually observe the force itself. It is essentially the force impact that dpdt has on a system. In addition, the observed motion of a star will only occur in this situation provided. The position, velocity, and momentum data will only result from a black hole with the mass that I determined already. So it is not possible to find a value for the mass of the new black hole that is different if the motion of the star remains unchanged.